In this video, we are going to talk about some applications of quadratic functions. So these applications that we're going to talk about mainly involve one-dimensional motion problems. We'll have some object that's moving around. I think most of the problems that I saw in Newton were about something being shot straight up into the air and falling back down to earth. So um, so that's what we're going to talk about here, and we're just going to go over a couple of different examples. And the Newton problems looked uh, like they were either one of these two types here. So, okay, let's get to it. All right, so in the first example, we have a model rocket is launched directly upward at a speed of 26 meters per second from a height of 10 meters. The function f of t equals minus 4.9 t squared plus 26t plus 10 models the relationship between the height of the rocket and the time of after launch, t in seconds. In this example, they want us to find the max height in meters that the rocket will reach and round to two decimal places. Okay, so they really probably should call this h. That would probably make a little bit more sense. H for height. And you might notice they are using the variable t instead of the variable x, and that's because here they're talking about time, t for time, right? So they have a rocket and they fire it off. They don't say this in the Newton problems, but the time starts at 0, right? So they really kind of should add here that that t is greater than 0, or greater than or equal to 0. Okay. And so, in other words, before you have some rocket sitting there, and then you hit the power button, and then it fires the rocket off. So before you hit that power button, this model doesn't really apply to it. So that's why we're only considering time starting from 0 and kind of moving forward. Okay, over in Desmos, I have this equation or function already typed in, and I have a little demonstration. So this red dot is the rocket. You're gonna see exactly what happens. Let's just go ahead and fire it off, and you're gonna see it goes up into the air, right, and then it kind of falls back down into the ground. So you'll notice here I have S instead of a 0. That's because T in Desmos is reserved for something else. You can see my graph kind of like goes away. It won't do it. Although I wonder if I change that variable if it might work. But anyway, just pretend S is for seconds, okay? But really it should be t, so don't worry too much about that. But this is what happens. I have a rocket. It's sitting on a platform 10 feet above the ground, or meters, whatever the thing is measured in. It gets fired off into the sky, goes straight up, and then it comes straight back down, and it'll hit the ground eventually. Okay? So that's it. Now the model does keep going. That doesn't mean that the rocket like burrows into the earth, right? As soon as the rocket impacts the earth, then that model is no longer valid, right? So it's not what happens. And here it's reversing time, which it just does automatically. You can control that and the speed of your simulations by adjusting these parameters right here. These are some new ones. So you can see the rocket goes up. And falls back down to earth. And so right as soon as it hits the ground, right, the simulation really is over with. All right, and their question to us is, how high does the rocket go? Oops. All right, we can grab a hold of this and get pretty close on Desmos. So right around in there, it looks like the height, just judging by this, is 44.38. and I guess that's in meters. Yeah, in meters. Okay. Okay. So then the question is, all right, fine, but how are we going to do this if we don't have Desmos to do that? So what we're going to do is we can take a look at this equation here, and like this is an actual equation of motion for some problem that looks like this. The one thing that this model doesn't take into account is, say, like air resistance of the object that's moving or anything like that. So this is an actual, this comes straight from physics, F equals ma, and the acceleration due to gravity in meters per second squared is half this value here. So, and this is the height at which it jumps off. So this is a not completely accurate, but a good first attempt at an actual model for this kind of problem. Okay, so and then we could see if we actually graph this out, right? There's what the actual graph of that thing looks like. It's a quadratic function, right? A parabola. And that's not the path that the object is taking here. That would be two-dimensional motion if the path was this. The actual path, right, of this object is it goes straight up, right, and then straight back down. The graph of this parabola is just giving us the height off the ground. So we can see at the max height right here, that is going to be the vertex of the parabola. So all we have to do, right, to find the max height of this rocket is to find this number right here, the second number, the y-coordinate of the vertex of the parabola. So that's it. So this problem really is nothing more than finding the vertex of the parabola. So let's go back and look at how we would do that. All right, so we would do it just like we have done before, right? We would know that A is negative 4.9. B is 26, right? And we would know that minus B over 2A is minus, and then 26 over negative 4.9. And whatever that comes out, oh, sorry, 2 times negative 4.9. So let's go to Desmos and punch that in, see what we get. So minus 26 over 2 times negative 4.9. All right, we get that value there, right? And so what we're going to do then is to take and plug that number back into this function right here. So if you're using your calculator to do this, just make sure you take a few extra decimal places. Don't round off too much, because then when you plug your answer into Newton, if you round it off too much, then it will affect the decimal place to where they want it rounded off. So you can see if you rounded it off to, like, to get the exact value, I could just on Desmos just do this. So you can see if you rounded it off too much, 2.65 or 2.7, let's say you rounded it off, that's going to affect this answer, and Newton would probably mark that wrong. So just make sure you take a few extra decimal places on this one. It's 65306, and then you'll be good. You can see that's really close to the value that Desmos is getting already. All right, and so that will give us the y value of the vertex there. Okay, and so we get 2.653. So what that number indicates is that 2.653 seconds, right, after the rocket is fired off, it achieves its maximum height. Its maximum height is 44.49 meters, and that's, you can see, rounded to two decimal places there. So that would be the answer, 44.49 meters. Okay, so that's it. So let's make sure that we answer the question completely. Find the maximum height in meters that the rocket will reach. Okay. All right. So the answer here is 44.49 meters. All right, next example. All right, so pretty much the same setup. A model rocket is launched directly upward at a speed of 26 meters per second from a height of 10 meters. The function f of t equals negative 4.9 t squared plus 26t plus 10. Models the relationship between the height of the rocket and the time after launch t in seconds. So far everything has been the same as in the previous example. Here's where it changes. It says, when in seconds after launch will the rocket hit the ground? Do not round until the final answer. Then round your answer to 2 decimal places. Okay, so they want to know when it hits the ground. Okay, so if we go back to our example here, I'm going to clear this stuff out. So we're starting at time 0. Right, the rocket goes up. And it comes back down. And the height of the rocket when it reaches 0 right, that one a little past. So I can only get so close in Desmos. Let's see. All right, that looks about as close as I'm going to get. So that looks like 5.67 seconds, right? About when I would do that. Okay, so we can get that, by looking at Desmos and kind of messing around with the simulation here. But how would we find it without Desmos? Well, if we take a look right at the graph of the parabola, we can see that looks really, really close, right, to the y-intercept. In other words, what we're doing right here to solve this equation is we're going to take this equation and we're going to set, remember f of t was representing the height, we're going to set that to 0, and then we are going to solve that equation. Okay. All right, and so that's how we are going to find that. Now, factoring that is probably a no-go, so my recommendation is just to use the quadratic formula. So let's go ahead and do that. So it would be, our A would be, oops, can I write on this? Nope. All right, so our A is negative 4.9. Our B is 26. Our C is 10. All right, and so what we do is put that in the quadratic formula. X equals negative B plus or minus square root B squared minus 4AC all over 2A. All right, so that's going to be negative 26 plus or minus B squared minus 4 times A times C. Wow. All over 2A. Man, that was hard. Okay. So we would enter that in, and what they mean, is don't round these calculations out too much. Like, when you type this in, you're going to get, some decimal number. And then when you square root it, you're going to get a decimal number. So you need to be really careful about how you do that. If you round those intermediate calculations, it's really going to have an effect on your answer there. So it's probably best if you just try to enter the whole thing as you would in parentheses here. Let's see if I'll do that in decimals first, and then I'll try to bring up the actually I don't think that's gonna work. So all right, so it's b squared, or negative b, right? Negative b plus or minus, so I'm gonna have to do this twice. Square root b squared minus 4 times a times c all over 2a All right, so that's what we get, and you can see we are getting a negative answer. That is this. I'm going to blow this up a little bit. That is this one right here. So remember what I said about the time starting at 0. So really, this answer just needs to be thrown out on this applied problem. Now, if the problem was find the x-intercepts of this function, well, then that is an x-intercept, right? But this problem applies to a specific real-world, situation where it doesn't make sense to talk about negative 3.6. That would be like negative 0.36 seconds before the rocket was fired. Well, this model doesn't even apply until the rocket is fired, which we are starting at time 0. So, so this answer just has to be thrown out for this applied problem. So the other answer with the minus you can see gives me the positive answer. That's this answer here, and that's very close to the answer that we came up with, just messing around with this simulation right here. And so it would be 5.67 to 2 decimal places on this one. So on this one, you would use the quadratic formula. And actually, this really shouldn't be x, but t, right? Since we're talking about time in seconds. So the time in seconds after the launch would be 5.67 seconds when it hits the ground. Okay? All right, and so in this example, it is using the quadratic formula to get the positive x-intercept of the graph that they give you. If you have any questions about how to plug this into your calculators, if you're having trouble doing that, let me know, and I will be glad to put up a video. I think I have a where I can emulate a TI-84 calculator, but that's probably the best that I could do. But anyway, just let me know if you're having problems entering that and getting the correct answer. All right, that's it for this video, and make sure that you do the, let's see, do I have? Yes, the assignment is this applications of quadratic functions Newton assignment. And again, that's due in 2 weeks from when I'm posting these videos, which is the 16th. So let me know if you have any questions.